numerical problem to find the current in the different branches of this circuit which is given. And also we have to find the potential difference between node B and node E. So here first we take this loop. This loop is A, B, E, F loop. This 2-volt battery. Suppose I current is passing through it. Then this rate is 1.5 ohm. Then 3.5 ohm. At this point B, this current is divided in two parts. It will go I1 in this branch BE and I minus I1 in this branch BC using the Kirchhoff's current law. So current in this branch is I1. This is I minus I1 and here I. Now we take this loop A, B, E, F. So we start from here, point A, then 1.5 multiplied by I current, then 3.5 multiplied by I1 because direction is same of the loop, plus 1.5 into I. This is also the same direction, so all are positive. This is equal to minus 6 because it is entering from positive to negative, so it is minus 6 volt, and here it is going from negative to positive, so it is plus 2. So we will add it, then it will be equal to minus 3I minus 3.5 I1 is equal to 4. Now we take the another second loop, which is B, C, D, E, B. Then 1.5 into I minus I1 plus 1.5 I minus I1, and this is in the same direction and it is in the reverse direction, then minus 3.5 I1. This will be equal to, this is minus 6 because it is going from plus to minus, it is going minus to plus 6. So plus 6 minus 6, this will be equal to 0. So this equation will be equal to 3I minus 6.5 I1 is equal to 0. We take this equation which was equal to minus 3I minus 3.5 I1 is equal to 4. We add it. So 3I cancel and it will be equal to minus 10 I1 is equal to 4, or I1 current is equal to 0.4 ampere. So we have determined the current I1 which is in this branch. Now we substitute the value of I1 here. Then 3I minus 6.5 into minus 0.4, this is equal to 0. So this will be equal to, I will be equal to minus 2.6. We subtract it, divided by 3, that is equal to minus 8.6 ampere. So this I current in this branch will be equal to minus 8.6 ampere. Now in this branch it will be equal to I minus I1. So we substitute the value of I and I1. Then I minus I1 will be equal to minus 8.6 minus of minus 0.4, which will be equal to minus 0.46 ampere. So in this way we have calculated current in this branch, current in this branch, and current in this branch. Now we have to find the potential difference between B and E. So we start from B. It is at a higher potential. So VB minus 3.5 into current is minus 0.4 as we have found here. Then it is entering from plus, so minus 6 minus BC will be equal to 0. So VB minus VE, this will be equal to 6 minus 1.4, that is equal to 4.6 volt. So potential difference between B and C we can find. So we are using only two rules here. One is the Kirchhoff current law for the current division at the node B and at C. At B, this I current, I1 this side, I minus here. At this point E, I1 current this side, I minus, when it will be again I current. And for the first loop and second loop, we will apply the Kirchhoff's voltage law and we can find the value of I1, I2 and also the potential difference between B and B. Now we take the next problem, that is a numerical problem for the balanced Wheatstone bridge. I have given this circuit, this circuit, this circuit, this circuit and this circuit and this. These all circuits are equivalent because here resistances are, here resistances are, here resistances are, here resistances are, and in the BD branch resistance R. So R product by this R into S will be equal to Q into R. So this is R into R square is equal to R square, means this is a balanced Wheatstone bridge. When balanced Wheatstone bridge is there, then there is no current in BC branch. So we can say that it is just like a open circuit. When there is no current, means it is a open circuit. So we can write equivalent circuit is this. This point is A, this resistance 1, this second resistance, and here, so R or R, 2R, and this 2R, both are parallel. So, by the resultant resistance between A and B will be equal to 2R into 2R divided by 2R plus 2R, that is equal to R. Now I give the similar circuit for this Wheatstone bridge. Here, when P and D are not connected or the potential difference between B and D is 0. So we can write this circuit as also this. Here B and D coincide here. So here current is 0. So here one resistance R, another resistance R, this resistance R. These two resistances are parallel and these two resistances are parallel. And these are in series. So parallel में कितना होगा? R and R, R by 2, R and R, R by 2, and R by 2 and R by 2 are in series. So this will be total. Now the same circuit, it can be also given like this. Here this point is A. Here resistance R, here resistance R, here resistance R, here resistance R, here resistance R. This resistance is between A. We compare it here, we will take this point A, this point is A, and this point is B. So this resistance is here. Here this resistance is A and this is at D. So this is here. Again this point is C and D. This is C and D, and this is A and B and C. So this is equal to there. So when you get the 5 resistances, 1, 2, 3, 4, 5 in this shape, this is just a representation of the Wheatstone bridge, which is balanced Wheatstone bridge. So its resistance will be equal to R. Now one more fashion we can use it. Here what we have done, here resistance is R, here resistance is R, here resistance, and this point is A is here, B is here. So you just pick up, invert it from here to here. This point is here to there. So this branch will be here, this branch will. So this will nothing but a Wheatstone bridge. So the resistance of this Wheatstone will be also equal to. So the resistance of this Wheatstone bridge between A and B is R. This resistance A and B is R. For this and A and B, resistance is R. For A and B, resistance is R. And for this A and B, resistance is R. So these all circuits are of the same type and they are Wheatstone bridge and the resultant resistance between two ends A and C, this end is R. Now we take the next problem when the Wheatstone bridge is balanced, but we have to find the X resistance which is parallel resistance. So here the resistance is 10 ohm. Here resistance is 5 ohm. Here resistance is 20 ohm. Here resistance is 5 ohm. So here when they are parallel, then resistance will be equal to 20 into x divided by 20 plus x. So P is equal to 10, Q is equal to 5, S is equal to 5. So P into S will be equal to Q. So P's value is 10 into 5. This is equal to 5 into S is 20 into x but at 20 plus x. We cancel it, we cross multiply and we will get x is equal to 20 ohm. So we can solve it and we will get the 20 ohm. We can also confirm it. 20 ohm and 20 ohm parallel means 10 ohm. Then 10 into 5, 50 and 10 into 5, 50 means your answer is correct. So you can verify your answer because the 20 and 20 they are parallel, so resistance will be equal to 10. 10 multiplied by 50, 10 multiplied 50. So they are equal means it is a correct solution. Now we take the another case when X resistance is in series. Here X resistance in series with this. So here the resistance is 100 ohm. It is 100 ohm, it is 10 ohm, this is your 5 ohm and here it is 5 ohm. So the resistance in this circuit will be equal to 5 plus X. So P into X, P is your 100, S is your 5, Q is equal to 10 and R is equal to 20 plus X. We solve it and we will find X is equal to 30 ohm. So in this way we can find the unknown resistance whether it is in the parallel or it is in series. When the V distortion is made, we simply with the P beta Q is equal to R beta S or P into S is equal to Q into R and solve these problems. Potentiometer is the last chapter or last section of the current electricity. It is very important from examination point of view and from the practical point of view because it is very important in theory as well as there is a practical in physics. So what is potentiometer? Potentiometer means it is a device which can measure the potential difference and EMF. Now we can also measure the potential difference and EMF by voltmeter. Then what is the difference? The difference is the measurement done by the potentiometer is most accurate and correct. It means the voltage or EMF, potential difference or EMF measured by the potentiometer is always reliable and exact. So potentiometer is an ideal voltmeter. Now what is the condition for the ideal voltmeter? The condition for ideal voltmeter is its resistance should be infinite. When the resistance is infinite, it means there is no current. So it is also based in null method or no current is passed when we take the final reading. Now voltmeter. Now voltmeter, as we know that what is the voltmeter? Voltmeter is converted by connecting a high resistance in series with the galvanometer. The value of the resistance will depend on the range for which voltmeter is to be used. So now the high resistance is in the series. So when we connect the voltmeter across the terminal of battery, then it will take some current. If there is no current is there, then there will be no deflection in galvanometer. It will take some current. Means there is some leakage of current or some current is required for the voltmeter. So it takes some current, means the current is not zero. So voltmeter does not give exact potential difference or exact EMF, whereas potentiometer does not take any current from the circuit and it is based on the null deflection. Null deflection is there when current is zero. Therefore, potentiometer is an ideal voltmeter and it will give most reliable and accurate value of the potential difference and EMF. Then why we use voltmeter? We use voltmeter frequently. Why? Because number one, the size of voltmeter is very small. You can have it in your pocket and it is very convenient to use. Whereas potentiometer, size of the potentiometer is nearly 1 meter and you have to have battery, then rheostat and all the, and you have to take the calculation. Here in voltmeter we get the direct voltage and here we will have to calculate and find the value of the potential or EMF. So voltmeter is convenient as well as its size is less. So voltmeter is generally used to find the EMF and potential difference, but potentiometer is used to find the potential difference and EMF where we want to find exact value of or accurate value of potential difference and EMF. Now what is the construction of potentiometer? Now potentiometer, we have a very long wire, 5 meter to 10 meter. It can have we can have 5 meter, we can have 10 meter, we can have any value length between 5 to 10 meter. Resistance wire. This resistance wire is made up of constant or eureka or why? Because their resistivity is high and their temperature coefficient of resistivity is low. So we will use the wire of either constant or eureka and its diameter or its area of cross section should be uniform. So I have taken 5 meter wire, 1 meter, 2nd meter, 3rd meter, 4th meter. The ends of these ends are connected by a copper strip. These ends are connected by the copper strip. Here also copper strip. Here also copper strip. Because the resistance of copper strip is negligible, so we will have the resistance only of 1 meter and 1 meter, 1 meter, 1 meter and 5 meter only. So at the end A and B are fixed and we have a screw here, and so this is the construction of, and here also a meter scale is given here to measure the length. So first of all we will consider this entire system is fixed on a wooden plank. Now we will first take the primary circuit. Primary circuit, this is the AB wire. I have just shown only one wire. Its length is 5 meter or 10 meter. It may be anything. It is made up of constant or eureka or nichrome because their resistivity is high and their coefficient of temperature coefficient of resistivity is very small. So its temperature, if temperature changes, the resistance will change negligibly. Now here, this point is A, E connected to battery, whose EMF is E. If small r is the internal resistance of this battery, here there is a key, here if we have a resistance, and here we have a rheostat and connected to. So A and B, these are the two ends this end and this end of the potentiometer, they are connected in series with battery, with EMF is the internal resistance small r, then the key, then resistance capital R, and rheostat whose resistance is RH. The resistance of RH will vary from minimum to maximum. So this is the primary circuit. Now we have to find the current in the primary circuit. The current in the primary circuit will be equal to EM of the battery divided by the total resistance. Now what will be the total resistance? Since this resistance and resistance of wire, they are in series. So the total resistance will be equal to the internal resistance R plus a capital R resistance if there is there. RH is the resistance of the rheostat and Rw is the resistance of potentiometer bar. So this will be the current in the primary circuit. Now basic condition is in the primary circuit current should be constant. Current should be constant. It means this should not be a cell. You should not use dry cell. You should not have Daniel cell. You should not have Lagrange cell because their EMF is not constant. So we will have to use a battery, which is a secondary cell and whose EMF is constant and internal resistance is also small. Now here I have given a general case when we have considered small r, capital R, RH. Now here small r can be 0. It is not given. Capital R may be 0. RH may be 0. But Rw cannot be equal to 0. So we take this circuit and we find the potential difference. First we will find potential difference between the two ends, A and B ends of the potentiometer wire. This end and this end. So this will be equal to current which is passing, that is the IP, which is the current in the primary circuit multiplied by the resistance of the potentiometer wire. So IP into resistance, so this V will be equal to IP into Rw, where Rw is the resistance of potentiometer wire. Now we define the potential gradient. Now what do you mean by the potential gradient? Potential gradient is potential drop on unit length of potentiometer wire. So once I again repeat it, because it is a very important definition. Potential gradient, which is given by X, it is drop in potential per unit length of the potentiometer wire. So this wire is A to B, and here from A to B the potential is capital B. So X potential gradient will be equal to capital B with the potential difference between A and B divided by the total length, which is equal to capital L. Capital L is the total length of the potentiometer wire from A to B. So X will be equal to V divided by L. So naturally what will be the unit? Unit of potential gradient will be equal to volt divided by meter. If we take the length in centimeter, then the unit will be equal to volt divided by centimeter. So X is equal to, this is the one way to find the X. Second way, X is equal to, we substitute the value of IP. IP is equal to EMF of the battery divided by R plus capital R plus RH plus Rw. This is IP into Rw divided by L. Similarly, we can write X is equal to IP into Rw bata L. IP into Rw, that is V bata L. And Rw bata L is also known as Rm, which is resistance per unit length of the potentiometer wire. This is also equal to IP into rho bata A. where rho is the resistivity of the material of the potentiometer wire and A is the area of cross section. So we can find the X by this formula, and by this formula. So I give the problem to find the potential gradient for this given circuit. Then in the given circuit, we have the EMF of battery is 2 volt, internal resistance is 1 ohm, RW is 10 ohm, length is 10 meter, and RH is from 0 to 40. Means the resistance of rheostat minimum is 0 and maximum is 0. So we have to find the maximum value and minimum value of the potential value. Since RW it is in the denominator, so RH is in the denominator. So X will be maximum when RH is equal to 0. X will be minimum when RH is equal to 40. So X minimum will be equal to EMF 2 divided by small r plus 40 plus 10. Because capital R is not given, so 10 multiplied by RW 10 divided by length 10. So it will cancel and we will get 2/51 volt per meter. This will be the minimum potential gradient. What will be the maximum potential gradient? Maximum potential gradient will RH is equal to 0. So X maximum will be equal to EMF divided by internal resistance RW 10 multiplied by 10 RW divided by L10. So this will be equal to 2/11 volt per meter. So in this way we can find the maximum and minimum value of the potential gradient. Maximum value will be when the rheostat is of 0 resistance, and minimum when resistance is maximum resistance, which is 40 ohm of rheostat. Now next problem, we have to find the potential gradient. Now here we have given IP, the current is equal to 0.4 ampere. The area of cross section of the wire is equal to 0.6 into 10 raised to power minus 6 meter square, and the resistivity is equal to 40 into 10 raised to minus 8 ohm. So R, we know the R is equal to rho L bata A. So R bata L will be equal to rho bata A. Or we can use this formula here. That X is equal to IP into rho bata A. We substitute value. So it is equal to 40 into 10 raised to minus 5 divided by A 0.6 10 minus multiplied by IP. IP is 4 here. So it will be equal to 0.4, which is IP, multiplied by, we solve it here, and it is 2/3. So result will be equal to 0.266 volt per meter. So we can find the potential gradient for if RH is given and if rho resistivity and area of cross section is given and the current in the primary secondary given. So in this way we can find the value of. So these two examples are important from examination point of view, and it has been asked many times in the board paper.